Okay, so I actually have 2 talks, so I decided to divide the topics in these 2 talks. So the first talk will be about the Lightcurve computation in binary microlensing. And there is no problem in inverting it with Scott's talk, because Scott's talk will more focus on fitting. But here we want to know how to calculate light curves. I think that after 2 days of this workshop, we have, oh, Scott is here. Okay. Oh, I just started. I don't know if you want to.
Probably makes more sense for me to go first. Yeah, it's fine. Whatever.
Okay. This is just calculation of the light curve.
Okay.
So I think it's not completely necessary. Okay. So I hope that after these 2 days of workshops, you have become more or less familiar with the shapes of the light curve you can expect from microlensing. You have learned what is a planetary caustic, a central caustic, a resonant caustic, and how the light curve looks like when you have these kinds of light curves. But up to now, you don't know how to calculate light curves. So I hope this talk will fill this gap, and I hope that after this talk, all of you will be able to go to your computer and write down a few lines and calculate the light curves yourselves, at least with your basic algorithm. Or if you are more lazy, you can just download the only existing public code for calculating microlensing light curves and play a bit with that. Okay, so our goal is this. So we want, given a lens model, we want to calculate the corresponding light curve, what we should observe if we point a telescope toward this target. So the problem is as you have been told that the gravitational lensing physics preserves the surface brightness of your source. So you see a magnification only because the images are larger than the original source. So everything is reduced to the simple problem of calculating the area of the images. Sum up the areas of all the images, and then divide by the area of the source. That's what we need to do in order to calculate the magnification in microlensing. So, but first we have to find the images, and we have to calculate their area if we want to plot the magnification. Okay, so I will go through several steps in this talk. First, I will show you how to calculate the magnification for the point source, so with a very small source. And so the main problem is solving the lens equation. Then I will introduce the finite source effect, because you know that stars, after all, are not point-like. And so I will also speak. I will speak a bit about the quadruple and hexadecapole approximations, and then we will go to the full calculations. And then we will see that there are 2 main options. One is inverse ray shooting, and the other is contour integration. Both of them have been introduced by Dave Bennett, so he also introduced these 2 main calculations. He focused more about inverse ray shooting because this is the method he implemented in his code. I will focus more on contour integration, actually, because it is the basis of my VB binary lensing, which is the public code I was speaking about a few minutes ago. So this is a public code that is available for anyone who wants to calculate light curves to an arbitrary accuracy. Okay, so first step, we want to calculate the point source magnification. So the first problem we have to face, we have to calculate the positions of the images. And we know that there is this, the starting point is this lens equation. Actually, you can see the lens equation in many flavors. And in the first few talks you have seen in different shapes. This is the lens equation in complex notations, which was introduced by Witt in 1990. Also, Dave introduced this lens equation in this shape. So in this lens equation, you have the position of the source, which is given by this Greek zeta, and then on the other side, the position of the images is given by z. Z bar is the conjugate, the complex conjugate of z. And then S is the separation between the 2 lenses. So these 2 terms are actually the deflection angles, the deflection angle of the first mass and the deflection angle from the second mass. And so, the two masses, okay, can be expressed in terms of a mass ratio Q. So that's all. That's all about notation. In this lens equation has been written in such a frame that the second lens is actually at the origin of the lens of the frame. So the origin of the lens plane is in the second mass. And there is a reason for that. I will say that a bit later. Okay, so actually, this equation, if you want to invert this equation, so if you want to find the position of the images for a given source position, you see that there is a complication here, because here you see that there is a z bar, not a z. So how do you get rid of this z bar? You have to use the complex conjugate equation. And so you extract a z bar from the complex conjugate equation, insert it here, and then you have an equation which only contains z without any z bar. So you can rephrase that as a polynomial equation. In the end, you end up with a fifth-order polynomial whose coefficients are given by this, well, not complicated formula. You can derive them using Mathematica, MATLAB, whatever you want. So it's just a quite easy task. So the problem is is finding the roots of these fifth-order polynomials, and there are standard methods to do that. So you don't have to invent anything new. Well, if you want, you can invent something new. It's always welcome. But in principle, for the complex polynomial, there is the so-called Lagarde method, which is so if you start from a given initial condition, then you can approximate the roots by taking several steps using this formula here, involving the first derivative and the second derivative of the polynomial. So see, this is a standard algorithm you can find everywhere, and there are many libraries implementing that. And so once you find the first root, what you have to do in order to find the next roots, you have to divide the polynomial. So you have to make the division of the polynomial, and then you are able to find the next root. And so by reducing the polynomial step by step, you will get all the 5 roots of the polynomial. There is a subtlety here, because after all, when you divide the polynomial, you introduce numerical noise. So in the end, after you find the 5 preliminary roots, you have to polish them. So you have, this polishing is done using the full original polynomial without any additional numerical noise. So this is just something you have to do in order to be more accurate. Okay, and then you can find the full algorithm in numerical recipes, for example, using z-roots and Lagarde functions. So this is something you can find even on the web, actually, but apart from some license issues. But actually, the last line just went off to the screen. In fact, I can see it here, but not here. But anyway, there is in the microlensing context, actually, there has been a new implementation, a new algorithm, which is an optimization of this algorithm, which was published by Scoren and Gould in 2012. And you can find it at this URL, which is below the slide. You can, I think you will receive the slides, so you can get it from there. Or you can just type Scoren and Gould, and you will find the web page on Google. Okay, so this is actually an algorithm which is more robust than z-roots, and it is slightly faster, actually. So it's something you can consider. Okay, moving on. Now that you know that there are caustics, actually, in gravitational lensing. And so you know that there are regions in which you have 3 images, and there are regions within the caustics in which you have 5 images. So how this is possible? Actually, this comes from the fact that, when we have manipulated the lens equation by replacing z bar using the complex conjugate, in practice, we introduce spurious solutions. So after you have found the 5 roots, you have to check that they are solutions, and if there are any spurious solutions. And so it's very easy. Just insert these roots in the original lens equation. If they solve the lens equation, they're images. Otherwise, they're just spurious roots. And after that, the last step is calculate the magnification for each image. And this is quite easy because you know, as I told you, that gravitational lensing preserves the surface brightness. So the ratio of the area of the image to the ratio of the source is just given by the inverse Jacobian. It's just a normal transformation, the normal transformation you have to do to solve an integral in which you want to change the variables, after all. You have to introduce the Jacobian determinant. And so after, in the end, the magnification is just given by this formula, and this quantity is quite easy to calculate. And so in the end, you can calculate the magnification of all the images, and you have the quantity you want to plot. And so that's all for the point source magnification. After all, not so difficult. You can do it with whatever language in which you have a standard library for solving the polynomial, for example. OK, now, now there is a complication, because we know that actually finite source effects are important. If we had a point source crossing a caustic, we would have a spike with infinite magnification, which is completely unphysical. So if you want to plot a light curve that crosses a caustic, you have to take into account finite source effect. So you have to take into account the fact that your sources are not point-like, actually. So, you can try to do the direct integration of the magnification, because after all, this would just be an integral over this disk of the quantity that you are able to calculate, but this is completely hopeless, because you will have an integral over a diverging line, so it is impossible to have it stable. So this is not a good route for calculating the magnification. If you are far enough from caustics, you can do something quite simple. You can just Taylor expand your magnification. And after all, this is not so difficult. This can be done almost analytically. So this is an expansion of the magnification, including the source radius up to the 4th order. And this gamma is the linear limb darkening gamma, if you are familiar with that. It was also introduced in several talks. So in principle, you can use this approximation and approximate your magnification using this formula. How do you calculate these terms, these coefficients A2 and A4? Well, you can just evaluate the magnifications at the boundary of your source on 4 points. And so combining the magnification at these 4 points here, you can get this term. And then you can obtain this A2 rho squared just by using this calculation. So this is the so-called quadruple approximation. You can go a bit further and try to also to account for the 4th order term. And in this case, you need 12 points, 12 more points, because you need 3 combinations, the red, the green, and the blue one, in order to find all the terms you need in order to calculate this 4th order term. So these approximations actually can be good, but of course we are not. This cannot be used across caustics. Okay, you can also try to study the validity of this approximation. So this is just a map of the lens plane, of the source plane, sorry, in which you can see that if you're requiring an accuracy of 10 to minus 2, then you can be happy with the point source approximation if you are here in the white regions. The quadrupole will actually be needed if you are in these light gray regions, and the hexadecapole approximation is needed in these dark gray regions. And the full calculation, in which you don't do any approximations, is needed only when you are across the caustics, actually. Okay. This is quite instructional because it shows the range of validity of different approximations. And consider that these simple approximations are relatively faster than the full calculations, are much faster than the full calculation. So you might want to implement that if you have to do heavy calculations with many, many points. And of course, you can change, this was done for the 0.01 source, which is a giant source, which is typically a giant in the red clump of the bulge, for example. This is for the more main sequence star, something like that, or not main sequence. turn-off point of a main sequence star, and you can see that everything becomes linear. So in principle, the point source calculation is sufficient almost everywhere, say for a very thin region around the caustic. So this is quite impressive. But actually, most of the information is actually also is actually contained in this region. So you have to go for the full calculation if you want to extract all the parameters correctly. Oh well, if you have 0.1, then you have to go with the full calculation everywhere, of course. But it is an exaggeration in some sense. OK, now let's go to the full calculation methods. As I told you, there are two main routes to get the magnification for the binary Lansing. One is inverse ray shooting, and Dave also explained this method quite thoroughly in his talk. So the idea is that after all, if you have an image in Z, it's easy to calculate the corresponding position of the source. You just put the value of Z here, Z bar here, and you get the corresponding position of the source. That means that if you have a point in the lens plane Z, it's easy to calculate the position of in which you have to put the source in order to have an image here. So after all, if your source is not here, but it's here, this means that here you will not have an image. And in order to find the image, you can make a scansion of the lens plane. So you can scan all points in the lens plane, and sooner or later you will find some points in which your calculation will give you a point inside the position of the source. So that's all. It's quite direct method, a brute force method in some way, because you're scanning all the lens plane in order to find this small object here, this small image here. But nevertheless, it's a very robust method after all, because in principle you can everything is under control, and it's very easy to do. And after all, by scanning the whole lens plane, we can find all the images, and the area of the images, which is the quantity in which we are interested, because we want to estimate the ratio of the area of the images to the area of the source, is just proportional to the number of light rays landing on the source when you do this scansion. So if you are scanning your lens plane with a grid, just the number of light rays that will land in the source after this inverse ray shooting is the result you're looking for. So it's a very simple and direct method. And furthermore, limb darkening can be immediately obtained, because you should just weight each light ray with the brightness of the landing point in the source. That's all. So if your light ray is landing in the center, of course, it will weigh more, because there the source is brighter. If it's landing on the limb, it will weigh less. So you just have to weigh your light ray with the source profile. So it's also limb darkening is very easy to implement. Okay, so in principle, every ray requires little computation, just this lens equation, but in order to be accurate, you have to shoot many light rays on this lens plane, so it takes a lot. So that's the bad thing. Okay, but one of the funny things about inverse ray shooting is that as a byproduct, you can obtain these magnification maps. So these are just obtained by an evenly spaced grid in the lens plane in which you are shooting rays, and these rays will land in different points in the source planes. And so they will design these funny shapes in which you can recognize the caustics, also the lobes around the cusp, so in which you have a higher magnification. And you have a higher magnification there because there are many light rays that have landed there. So once you have a magnification map, then it's relatively easy to calculate a light curve, because you just have to slide your source through your chosen trajectory, and then count the number of light rays that are inside your source. So here, here, and here, you will get different results depending on the number of light rays that are contained in this in this source disk. But after all, it's relatively easy. And furthermore, you can use the same magnification map and calculate many light curves. That's a great advantage because the big calculation is already done, and then the sliding a source is not so difficult after all, and you can get many light curves with little effort. And so this is useful if you have to do a broad search in the parameter space because it's cheap. If you're doing that with fixed S and Q. In fact, these magnification maps only depend on two parameters, the parameters you have on the lens equation, the separation between the two lenses and the mass ratio. If these are kept fixed, you can obtain light curves by varying all the other parameters. Okay, but you know that this is not always possible. If you have to change S and Q, in principle, you should generate magnification maps at each step. So, but this is, of course, very expensive. And Dave Bennett already introduced you to this image-centered ray shooting. So in this algorithm, first you calculate the centers of the images by solving the lens equation as we did with the point source case. And then you construct a grid only around the position of the images. So you don't shoot light rays everywhere in the lens plane, but only around the centers of the images. So in this way, you don't have to shoot too many rays after all. And furthermore, you can even go to polar coordinates, as explained by Dave, and then the number of light rays can be relatively small. Okay, there are also other algorithms based on inverse ray shooting. For example, there is Subodong in 2006 proposed that high magnification events when you have high magnification events, what happens is that the source is passing behind the central caustic. So in principle, all images are more or less on the Einstein ring. So that means that your images will be very elongated arcs around the Einstein rings. So you don't need to shoot everywhere your light rays. You just have to cover this Einstein ring very accurately. And so this is what Subodong implemented in 2006. But he also developed another algorithm for the general case instead. His proposal is to calculate the boundary of a circle that is much bigger than your source. Well, it is relatively bigger than your source. So if you have the boundary of this circle around your source, you will have the corresponding circle in the lens plane, and you have to shoot light rays only inside this circle, and you will cover your image. So this is what's called loop linking methods. So in this case, you just shoot light rays in this region in which you expect to have the images, so you don't shoot light rays everywhere. So it's similar to this algorithm, but in this case, it calculates the boundary of this circle around the image. So, and also in other funny things, so you can collect light rays in hexagonal pixels, and so instead of counting light rays, which may be a lot, you can just pack them into some number of pixels, and so this is much faster. So many possibilities for optimizing these basic algorithms. And another important thing about inverse ray shooting is that it is possible to implement them on GPUs, because after all, shooting light rays, it's the same operation that you repeat many times. So this is a typical problem in which you can use GPUs. And so in this case, there has been an implementation on GPUs by Joe Ling in New Zealand, and so it can obtain magnification maps very quickly because it's implemented on the GPUs. Of course, if these magnification maps are not reused, you still have to go to other methods such as image-centered shooting or something like that. Okay, so this is just a table of advantages and disadvantages of this inverse ray shooting. So the basic operation is very simple, individual rays. very easy to shoot. And then you can reuse magnification maps. It incorporates limb darkening. It can be implemented on GPUs. But if you, the disadvantages is that it scales the area of the images. So it's a large number of layers is typically required. And furthermore, if you have smaller sources, you also need a denser sampling, which can make the calculation painful. OK, now let's go to the other method, the contour integration method. So the idea is to rephrase the area integral we had here as a line integral along the boundary. You know that there are theorems in mathematics that relate the area inside the closed curve with an integral along the line. So in principle, what we have to do is just to find the boundary of the image and not sample anything inside the integral. So in principle, you can expect that it can be faster because, after all, it's better to do a one-dimensional integral instead of a two-dimensional integral. This is in principle true. It can be faster and very elegant, but there is also a lot of work to do in order to keep everything under control, actually. So the basis of contour integration is the so-called Green's theorem. So as I told you, this is the one-dimensional integral along the boundary, and this is a surface integral inside the image. And in principle, if you are just interested in the area, which is what we want to do, you have to choose this function here, such as this quantity is equal to 1. Actually, you have several possible choices for these two functions, and correspondingly, you will have different expressions for the line integral, but all of them are equivalent. You just have to choose the one you want. Actually, if you look at the first one, this is just the integral of x2 over dx1, but this is very familiar to us because this is just what you do when you do the integral of a function. So if you go from this point to this point, you are getting the area below the function. But then when you go back, you cover the other branch. And since you are going back, you are changing the sign. And so summing the two contributions together, you have the difference between the two areas, which is just the area of the image, after all. So it's something that you should know from, from the first year of your bachelor, after all. OK, now, so the problem is that now we have to sample along the boundary. So of course, you can do that just by taking the center of the source and then adding the source radius times a phase factor. This is a complex phase factor that allows you to go along the boundary of the source. So this is for sampling the source. And now, for each point along the boundary, you have to calculate the corresponding images in the lens plane. And so for each point in the boundary, you have to use the algorithm for solving the lens equation. So, and of course, this is the slowest step in this algorithm. So, in principle, once you sample the source in the source plane, you will get the boundaries of the images in the lens plane. So this is the critical curve corresponding to this caustics. I think that you have mainly seen caustics, but actually caustics are derived from critical curves, which is something maybe you have not seen as much as acoustics. OK, now the problem is that once at each step, you have to decide how to assign the new points you have obtained. So for each red point here, you get 5 roots from the lens from the polynomial, and you have to associate each point to the correct image boundary, which is not trivial. Because you need an algorithm to say, OK, this point should go to this image and not to this one, and so in order not to confuse the boundaries of the images. And of course, the simplest thing to do is to use a least distance criterion. So you associate the new points that you have found with the boundaries you have already calculated using the least distance criterion. So if this is the closest point to this one, then you say, okay, this is the continuation of this boundary. And if this is the closest point to this one, you have to associate with this one. But there are situations in which the things are not so simple, and you also have to check for the parity, actually. For the parity of the region. I didn't tell this in this slide, maybe later. Okay. Now, if the source is actually crossing a caustic, then at some point you will find two new images popping up, as in this case. So now you have two new routes, and of course this will start a new boundary here. So of course, you have to. You can recognize it because you have two more unmatched routes that do not match any other images. And the same happens at the destruction of two images. And of course, we have to keep track of this pairing, because once you start a new boundary from this point B, another new boundary from D, you have to keep track on how these boundaries are paired, because this is necessary in order to do the integration in the end. So this is something you have to do, we have to keep in mind for the next few slides. So for example, you have to keep track of these 2 points here, and that they are actually associated. Okay, now once you have constructed your boundaries, you can perform the integral. The integral, if you use this form of the integral with the wedge product, which has some advantages actually, this can be approximated by a discrete sum over the axis that you have calculated. So for each segment in your boundary, you have to do this wedge product, which after all is simply simplified to this form. So it's a quite simple form. So what happens is that actually you are calculating the boundary, and you are approximating the boundary with a polygon, actually. So it's not a curve. It's no longer a curve. Now it's a polygon. And of course, this means that the area is typically underestimated if you have a convex shape. But there are situations like this in which it's actually overestimated. So there are some exceptions. So this is what happens if you have a basic contour integration. And furthermore, the last thing to say is that actually, we have to multiply the result by the parity of the boundary, because you need to go counterclockwise. And if you have a negative parity images, then you go clockwise. So you also have to multiply by the parity of the images. And the last thing is that if you have created, if you have a source that is crossing a caustic, you have two unclosed, two open boundaries, one here and one here. And finally, you have to connect them in order to have a closed curve. So that's why you need to keep track of the two images that have been created here and then they've been destroyed here, in order to put the correct reconnection terms in order to close the polygon in this case. So as you see, there are many tricky parts in this algorithm. Okay, so well, this is just I just sum up all the things that I said here in these few sentences. As you can see, you have to run a route finder for each point in the source boundary. Then you have to put the routes in the correct boundary and keep track of creating and destroyed images. Then you can calculate the integral by polygonal approximation, and then you have to sum the contour integral through the correct parity, including connection and destruction term. So that's all for the basic algorithm. But in the end, one thing you have to do in some way is also you must estimate the level of approximation of your approximation. So at some point you have to calculate the error you are committing with your approximation. So since the time is running up, so I will go fast on this topic. But anyway, it's possible to estimate the error you are doing by approximating a continuous integral by discrete sum. This is something you can do, and after all, you end up with an error term that is cubic in the length of your arc. So for each arc for each arc that corresponds to some delta theta in your phase factor along the source boundary, the error you are committing by replacing the continuous curve with a straight line is of the order is cubic in delta theta. Okay, but then you can think, okay, but maybe I can do a bit better than that after all, because I can try to introduce higher order terms in my approximation. This is possible, and actually this is the thing that I published in 2010, that it's possible to introduce higher order terms. So this is the parabolic correction, and you can see that it involves the first and second derivatives. You should not be scared from these factors, because actually these things are almost free, because they can be calculated analytically from the Lenz equation after all. So these wedge products actually are very straightforward to calculate with the knowledge of the Lenz equation. And after all, you end up with a residual which is fifth order in delta theta, which means that you are doing much better with a few points. This means that you can optimize your contour integration by requiring less points on the boundary, and then keeping the same accuracy, including this parabolic correction. Okay. In the end, it's important to keep track of the errors we commit at each step. So in my code, I have these errors estimators which work in a complementary way and keep track of all possible failures of the algorithm. And so the good thing is that once you have knowledge of the error that you are committing in your calculation, you can you can decide. You can also give a statement of the errors you're committing globally by summing up the error terms that you have at each step in your along your boundary. And if you are not matching the accuracy you want in your calculation, then you have to increase the sampling. But you can do it in a clever way, because you know the errors at each step in your calculation. And so actually, you have to increase the sampling only where it is actually needed. So if you start for an evenly spaced grid in theta, you see that the error is larger in this segment here. So you have to increase the sampling here. So we will put a new point here, and not everywhere. We will not increase the sampling all over the source boundary, but only along the arcs that need more need additional care. So we insert a new point, here, and then we just have to recalculate the terms that arise from these two pieces of the additional arc. So we don't have to redo the calculation for the whole the whole source, but only the calculation that is actually needed. Okay. The time is running up, so I will go very quickly on limb darkening. Limb darkening is not for free in contour integration, because in contour integration you can calculate the area doing this one-dimensional integral along the boundary, but this is just for the uniform sources. But if you want to take into account limb darkening, the only way to do is actually to calculate to divide the source in different annuli, and then to calculate the magnification of each annulus and weight it with the source profile. So this is the way to go. Also, this thing, I will not spend time on this. It can be done in a clever way, so that you actually increase the sampling only where it is needed. And so in practice, the source profile, the continuous limb darkening source profile, can be approximated by these steps here. And so you can increase the sampling only where it is actually needed. So in the end, we can you can also try to understand how many points you need, for example, to make a calculation at some magnification. So if you reach a magnification of the order of 80, you will need something like 300 points or something like that. But the number of points depends on the magnification. So of course the algorithm will be faster when you are at low magnification, and it will be slower when you go at higher magnification, because you need a larger number of points. But everything is done adaptively, and the calculation is stopped when the required accuracy is reached. Okay, well, of course, this is just a table of the speed-ups that are obtained by using the parabolic approximation, optimal sampling, and of course, if you include limb darkening, the code will become slower because you have to do additional calculation for each annulus. Okay, so last thing is I wanted to introduce you to this VB binary Lansing, which is the only available publicly available Microlensing code for the binary Lightcurve calculation. And so this code includes several tools, not only binary, but everything you need for basic Microlensing calculations. Also, higher order effects are already implemented, the linear limb darkening, annual space parallax, and circular orbital motion. It comes as a C++ library. It has been tested on all operational systems, and it's importable in Python. And the source code is available. It's public, even if I have not adopted any specific standard, so it's quite messy. So the package is available at this URL, and you will find the .h.cpp files, which are the core files, the main.cpp file, which include examples and instructions for the use of all functions, and and also other things. So these are things that are used in the example, and this is instruction for use in Python. Okay, so an example of use. You just import a library in C++ if you're familiar with C++. Then you declare the library here. Then, well, just give assign values to the parameters here, and just state the accuracy you want to reach. And then this is the calculation of your binary magnification. And you just have to call this function vbbl.binarymag. And so in the end, your mag will be the result of your magnification calculation. So it's very easy to use I think for everyone. And so contour integration, it's complicated. It's much more complicated than inverse ray shooting, because as you've seen, it's difficult to, in fact, I'm concluding. It's difficult to keep everything under control. And furthermore, limb darkening comes at a substantial cost. So that means that if you want to do a limb darkening calculation, probably then the code becomes much slower. But of course, it's much faster in general, and there is large feedback from the community also, which makes the code even more robust, maybe. Okay. Just to give you an outlook for what we need for the next few years in view of WFirst, WFirst will deliver an incredible amount of data, an incredible amount of new microlensing events that will need to be modeled. So, and we will also have multiple systems that will likely show up. So, for multiple lenses, inverse ray shooting already has several implementations, so they're already ready. Well, contour integration has never been tried beyond binary Lansing, and you can imagine why, because if you have more images, it's more complicated to do all this stuff, also reconnection and whatever. But anyway, there is still room for optimization, speed up, parallelization of different codes, and so new ideas are really very welcome, because the challenge we are going to face is really huge, and we need to do everything to have faster code in this very basic brick, which is the calculation of Lightcurve. Okay, I can stop here. Yes, I've encountered this problem, and in fact, this is the case in which the sampling is increased a lot around the cusps, because all these estimators I presented before with these error estimators are designed to keep track of these situations. So there is one of them, maybe the second one, as far as I remember, which is specifically designed to keep track of cusps. So in that case, the sampling is increased a lot, and so on. In the end, the linking is done correctly. I never do that. Because in principle, yeah. But I know that there are cases. Maybe one of the worst cases is when your source is tangent to a big-to-big singularity, which is even worse than a cusp. It's just a higher order singularity. Yeah, yes, in that case you have 4 images altogether. So this is one of the worst cases, and so I had to spend some time a bit in order to have the code working in that case. But anyway, I took care of that problem, so it seems to work fine. Yeah, but you can increase it. So it's something you can increase. You mean 10 to minus 2? Yeah, well, typically 10 to minus 2 is fine almost everywhere for the all cases. Well, of course, if you want to finalize your search for the best model, maybe you can go to 10 to minus 3. But in my experience, actually, it doesn't make a big difference. There are only few cases in which you need to go to 10 to minus 3 in my experience, actually. So, and when you go to a very high magnification events, then it's even better, because in that case, the an accuracy of 10 to minus 2 translates into something like 10 to minus 5 or a precision, which is much better than anything, any possible observations. No, it's 10 to minus 2, it's absolute accuracy. So at the moment, the code is done in absolute accuracy, not relative accuracy. There has been a request about the relative accuracy by Etienne, so I will implement also relative precision besides absolute accuracy. But at the moment, it only works in absolute accuracy. So it's 10 to, the magnification is 100 plus minus 0.01, which is much better than what you need, actually.
Okay, let's move on to Valerio.
Okay.